Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to electromagnetic theory. In the previous video, we discussed about the generation of electromagnetic waves through LC oscillations. In this video, we are going to discuss about another important concept related to electromagnetic waves, which is electromagnetic spectrum. Okay, so far what we have discussed, first we discussed the basic nature of electromagnetic waves. Okay, so we know that the electromagnetic waves, they consist of sinusoidal variations of electric and magnetic fields which travel in mutually perpendicular planes, and the direction of propagation of the wave, the electromagnetic wave, is perpendicular to those planes that we have discussed. So here the electromagnetic waves, the important thing to notice here is that they are sinusoidal variations, alternating quantities. So when a thing is alternating, oscillating, and can be expressed in the form of a sinusoidal expression, some important parameters come into play. Okay, the basic signal parameters. So here those basic signal parameters which come into play, they are, because the electromagnetic wave is it consists of two sinusoidal alternatingly variable quantities. So they are amplitude, frequency, phase, wavelength, time period, and propagation speed or velocity, whatever you want to call it. So here we have already discussed this in communication systems and also I think in data communications, that but here I will just, for to maintain a systematic discussion, I will explain this, but we'll go a little bit fast. Okay, so first is amplitude. So basically amplitude is the maximum value of the alternating quantity. Here in this case it is the alternating signal, the maximum value of the signal which it can have. So it is directly proportional to the energy content of the signal. Okay, so here the peak value, here for the positive half cycle it is plus A, and the negative half cycle it has the same value in terms of magnitude, but the direction is opposite, minus A. And here it is plus B, slightly higher, and same in the negative direction. And another important thing, it can have different values, different values with respect to what parameter or quantity we are measuring. So it can be for electrical quantities mainly current and voltage, and power, that also come into play. Voltage, current, and power, these three parameters are mainly measured in electrical systems. For others it can be different in mechanical, it can be displacement, velocity, everything comes into play, but we strictly will confine it to electrical systems. So voltage, current, power, these three alternating parameters are measured. So amplitude is the peak value of the signal, the maximum value of the signal in both positive and negative directions. Magnitude stays the same, direction is reversed. Then is time period and frequency, they are interrelated. So basically time period is the time taken by the signal to complete one cycle. So what is one cycle? One cycle basically is from the start, this is the start, the starting point, this, it goes one positive half cycle, the positive half cycle, then the negative half cycle, again back to the same position, that is 0. This is one cycle, one positive half cycle, one negative half cycle, 0, that is one cycle. So the time taken to complete one cycle, that is the time period, capital T. That is the time period. So definition of time period is the time taken by the wave to complete one cycle, one full cycle. That is one positive half cycle, one negative half cycle. Sometimes it can be first negative, then positive. It depends on the nature of the wave. So that is the time period. And what is frequency? Frequency is basically reciprocal of time period. It is the number of complete cycles, okay, number of cycles completed by that signal in 1 second. How many complete cycles it can go in 1 second. So here the time period or the time taken by the wave to complete one cycle is 1 second. That is, time period is 1 second. That is yes, the here the total here, the frequency is 2 hertz. Okay, the frequency is 2 hertz. So basically it means that in 1 second it completes 2 cycles. In 1 second it completes 2 cycles. So one cycle is completed in 1/2 seconds. So that is the time period. Okay, initially what I told, that was not right. Here the frequency is 2 hertz. It means it completes 2 cycles in 1 second. So here one cycle from here to here, again from here to here, that is another cycle. One cycle, 2 cycle, that is completed in 1 second. So in 1 second 2 cycle. So this is the frequency, and for one complete cycle it is 1/2 seconds. This 1/2 seconds. So that is the time period. Okay, so frequency is the reciprocal of time period. Time period is the reciprocal of frequency. Unit of frequency is hertz or second inverse, and time period is seconds, obviously. So you can express it in second inverse or hertz, and here it is reciprocal of frequency. Another thing, angular frequency. Angular frequency is expressed as omega, which is 2 pi f, and that is in radians per second. This is in hertz or second inverse. This is in seconds, and this is radian per second. This is angular frequency. Okay, angular frequency. Okay, then we have completed amplitude, time period, frequency. Then is phase. So phase basically is the relative position of the signal at the start, or the point where observation started. Okay, so here this is, let's say, the signal. Okay, this is the signal, and let's say we represent it as the signal as A is equal to A sine omega t, this. So here the phase angle, the initial phase angle, that is 0 degree, because it starts from the origin. It is the general representation of a signal is generally in this way: A sine omega t plus minus phi. It depends upon where the waveform starts. So suppose the waveform, one of the waveforms, it starts, let me use a different ink. Okay, one of the waveforms, it starts from here, sinusoidal, and it starts from here, like this, it starts. So here it is starting a bit early. It is starting a bit early. So here it will be A equals to A sine omega t plus phi, which represents phase lead. And there we have another waveform which is starting here. Okay, like this, here at this point. So here it is lagging. Okay, it is lagging. So this can be represented as A is equal to A sine omega t minus phi, that is phase lag. Okay, so this is the thing, phase lead and phase lag. So starting from here means it has already, this is the position. At this same observation point, the initial wave is from here, from 0. Here it is a bit afterwards for lag, and it is bit before. Okay, so that is phase lead, which starts early, phase lag, which starts afterwards, and just at t equals to 0, that is this. Okay, neither phase lead or lag, in phase. So this is all about phase. So for phase lead it is represented as plus phi, and phase lag it is represented as minus phi. Then comes wavelength. So wavelength basically is the distance traveled by the signal waveform in one time period. Okay, in one period or one time period. That is the wavelength of the signal. So basically here, this, let's say this is the time period, which is the time taken by the signal waveform to complete one cycle, that is from 0 to again 0. This is the time taken by the signal waveform to complete one cycle, and in this one time period, the distance traveled by the wave, that is this wavelength. Okay, the distance traveled by the wave during that one time period, that is wavelength. Okay, and here if we take wavelength by time period, if we divide these two parameters, is lambda by t, this gives us the propagation velocity of the wave. The propagation velocity of the wave, it can be written as lambda into 1 by t, which is lambda f, because f is equal to 1 by t. So v is the propagation speed or velocity of the wave. This. So we have discussed amplitude, frequency, time period, phase, wavelength and velocity. Now the main topic, which is electromagnetic spectrum. Why I discussed all this? Okay, so basically electromagnetic waves, it is a whole, it has a wide range, and basically it is classified or categorized on the basis of two parameters. First, it can be, because they are interrelated, it can either be classified in terms of their wavelength range, or it can be classified in terms of their frequency range. Okay, two styles, two approaches. Some people like to use the wavelength approach. They like to see the categorization in terms of wavelength, and some like to do it in terms of frequency. It depends upon the requirement also. Okay, so the charts which are available, the electromagnetic spectrum, it constitutes both wavelength and frequency. So basic definition of electromagnetic spectrum is that it is the orderly classification of the electromagnetic waves, either according to their wavelength or frequency. Okay, so it gives us a table. Now before you see the table, I want to tell you that these categorizations, they are not precise. They are not absolute, they are approximate. Basically what happens is that when we categorize the electromagnetic waves, we measure their energy, we detect a signal, there will be some fluctuations of the order of 10 to the power 1, 10 to the power 2, or 10 to the power minus 1, 10 to the power minus 2. Okay, so these minor fluctuations can be accommodated. Okay, so here these different categorizations, which are called as bands, okay, different range, they are called as bands of electromagnetic spectrum. They generally overlap. So there is a possible error value of 10 to the power 1 to 2, or sometimes 3, and here 10 to the power minus 1 to minus 2 to minus 3. So these can be accommodated. Okay, so this is just an approximate representation. So the different bands or categorizations of the electromagnetic spectrum, they are: first, the gamma rays, where the frequency range in hertz is from 10 to the power 20 to 24, and wavelength range is lesser than 10 to the power minus 12 meter. Then we have X-rays with frequency range of 10 to the power 17 to 10 to the power 20, with wavelength range from 1 nanometer to 1 picometer. Then the ultraviolet rays with frequency range from 10 to the power 15 to 10 to the power 17. So here it is from 400 nanometer to 1 nanometer. The visible rays, which is 4 to 7.5 into 10 to the power 14 hertz, and here the wavelength range is from 750 nanometer to 400 nanometer. Then the near infrared, 10 to the power 14 to 4 into 10 to the power 14, wavelength from 2.5 micrometer to 750 nanometer. Then near infrared, infrared, 10 to the power 13 to 14 hertz, and here it is 25 micrometer to 2.5 micrometer. Okay, and then we have microwaves, 3 into 10 to the power 11 to 10 to the power 13, and here it is 1 millimeter to 25 micrometer. And then the radio waves, which is generally it is lesser than 3 into 10 to the power 11 hertz, and the wavelength is basically greater than 1 millimeter. So here we will study the different bands, all of these in detail in relation to their properties, their applications, and the various characteristics we'll discuss in detail in separate videos. We will group some of them and we'll cover it in 2 or 3 videos. So this is basically the demarcation, the categorization of the different frequency and wavelength ranges of the electromagnetic waves, which is called as electromagnetic spectrum. Okay, so that's why I just gave you a quick review of the basic parameters or the basic elements of an electromagnetic wave or a sinusoidal wave, because electromagnetic wave are sinusoidal variations. So this is the thing. Also, we have covered this earlier, where the electric and magnetic variations are represented in terms of this, where the symbols, they represent the respective values. Okay, we have discussed it in electromagnetic waves basic concepts. Okay, so we'll discuss the various categorizations in separate videos by grouping them together. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.